Ooh, all right. Uh-oh. That's actually not the problem I want to start with. Hold on. This is the one I want to start with. Okay, it's 9 o'clock. Y'all ready to get started? Yep. You should have a take-home quiz on chain rule for me, yes? Today you have it, right? Sorry, I asked for it last time. So if you could, just pass them down to the center.
I have that emailed in with the 2.6 and 2.7.
You did what?
Oh, I have that emailed in the 2.6 and 2.7 for you.
Emailed to me?
Yes, sir. Or it's in the homework turn in.
Okay, I need, has to be a hard copy. Is that all right? I mean, can you print it out and like, get it to me next week?
Yeah, I have the copy. It's just in my office.
Yeah, if you could just bring it. Yeah. Oh, sorry, excuse me. All right, everyone here, good. Thank you. More down there? No. Yeah. Okay. I got it. Thank you.
You have mine on.
Got it. Okay, everyone. Where's everybody? Just, I think everybody here should just get 100 just for being here, yes?
Yeah.
We're just, really?
Yeah.
Tough it out, right? Tough it out. Tough it out.
No, like their speakers like 100.
So, I don't want to hear it. Okay. Nobody's told me anything. No one's told me I'm sick. I'm not coming to class. Okay. We're going to start with this example, related rates, right? So the main idea from last class is probably the most applicable thing we've done this entire semester, which is being able to take any equation, right? Any equation that exists out there and somehow create a relationship between the variables, the rate at which one changes and how that impacts the others. And we're using that to try and solve these things, these word problems called related rate problems, right? You know what? Am I on? I want to make sure I'm not muted or something here. Yeah, I'm good. Okay. So I'm going to try this. I don't know if it's going to work. It's kind of bright in here. But read the problem over there on the board while I get this set up. We have a street light, right, mounted on a 20-foot pole. We have a 6-foot person who's walking away from the pole. That person is walking at 7 feet per second. That's pretty fast, actually. And then the question is, how fast is his shadow moving along the ground relative to the pole when he is 12 feet from the pole. What? Okay, so I'm going to try this. All right, this isn't probably not going to come out too good, but here's our light pole, right? You've got a light, and we've got this person. Yeah, you're not going to be able to see a shadow. Yeah, I can see it. You can't see it. It's on. I was hoping I could do this and you would see the shadow projecting, but I have an animation for it. Okay, so that hopefully will make a little more sense once I show you the picture. I don't want to show you the animation yet, though. All right, I want to see if we can't come up with this without any visual guides. So you'll have those blank sheets that I gave you last time. Start setting this up. So I want you to guide. You know, you should bring us all tacos. No, I'm kidding. I don't know anything. So we have two pictures we're going to draw, right? The instant, and then we have the general picture. We have what we're given, what we want. Then we're going to need an equation, right? Then we're going to do implicit on that. And then we're going to try and solve the problem, right? That's basically the layout for these problems. All right, so where do you want to start? You want to start with the instant picture? You want to start with the general picture? You tell me. I wanted you to guide me a little bit more today than me guiding you.
Instant.
Instant? Okay, what do you want me to draw?
20-foot pole on the left.
20-foot pole on the left-hand side? Okay, here's a pole. It's light, right? Light. 20 feet tall. That doesn't change, right? Throughout the problem, 20 feet doesn't change. All right, can I draw the ground?
Sure.
Okay, I'm going to draw the ground. All right, what next?
Person.
I'm going to draw a person, okay. Any preference on color? I have red, I have blue, I have purple.
Purple.
Purple, okay. This person I'm going to draw is 6 feet tall, so, you know, just not taller than the pole, right? So 6 foot, somewhere around here, here's my person. Do you want me to get fancy?
Yes.
You want me to get fancy? Okay, I'll get fancy. There we go. Okay. Now, can I label anything for the person?
Yeah, that's height. 6 feet.
6 foot tall. That's not going to change either, right? So this person is 6 foot. All right. What else? This is the instant in time. So it's 12. This person's supposed to be 12 foot away from the pole. So it's not drawn to scale. I apologize, but you know we know that the distance from here to here is 12. All right. I'll put my units. Feet. I'm just going to put a little dash there. No, I better not. That's feet. It's all feet, okay? I won't put the unit. Anything else on this instant?
Line on where the shadow would be.
Okay, so you want me to actually put the shadow on here? Okay, so where would that shadow be? How would I do that? To the right of the person, the shadow's over here.
Starting.
Where's the edge of the shadow? How could I draw that? Is it 6 also?
No.
It's not 6. Where is it though? How could I draw? Is it way out here? Is it out here? Is it right here?
Probably triangle.
It's a triangle, okay? You have to see this triangle. You have to see that, imagine the light, right? All the light's coming up, and any light rays that hit his body, right, is going to be the shadow. But the light that goes over his head actually gets to the ground, right? So if you draw like a straight line from here down to the ground, right? Like this, his shadow should be on the ground like that, right? Something like that. Not bad. You can tell I've been doing this for a long time, right? This artistic ability here. Anything else on that? You happy with that? Okay. How about the general picture? Let me draw the things that stay the same, right? The pole, still here, 20 foot, right? The person is still 6 feet tall, right? Now, in this picture, I'm not going to get artistic. I'm just going to draw a line instead of the stick figure of the man. I'm just going to draw the man like this, okay? He's drunk. He's leaning over. There we go. Okay, that's my 6 foot man. Right, so this is 6, this is 20, but now this position from here to here is no longer 12, right? It can be arbitrary. It can be anywhere at this point because he's in motion, right? Were you going to say something?
I was just gonna say maybe 7 feet per second.
So 7 feet per second is how fast he's moving, right? So we don't want to label this 7 feet per second because that's not the length of something, it's how fast something's moving, right? But we could label it, right? We could call it what? X, anything, right? It's a variable, it's changing in the problem. The X is changing. Now the 7 feet per second is how fast it's changing, right? How fast it's growing. So I'm going to label this X, and with that knowledge, I'm going to put here dx dt is 7 feet per second. Do y'all get what I'm doing here? I'm labeling the length of this side, and as he walks, this length grows, and it grows at the same rate that he's walking, right? That's how fast that X is growing. With me? All right. I could also draw his shadow, right? If I wanted to. Shadow comes down, hits right here. Right, that's the tip of his shadow. So what is it that we want in the problem? We want to know how fast his shadow, and when I say his shadow, I mean the tip of the shadow, okay? How fast is the tip of the shadow moving along the ground relative to the pole? Relative to the pole. So here's the pole, right? It's like if you were standing at the pole just watching the tip of the shadow, how fast is that shadow moving, right? Got it? So I want the speed of something, right? I want the rate of change of something with respect to time. But what though, right? Like what? The change in what? Not X, right? Because X is how fast he's moving. So what do I need to do here? I need to assign a new variable, okay? And it needs to be, what? The shadow, right? S, let's call it S, all right? And it would be, where would S be on this picture? Yes? From here to here? No? From to the pole. All the way to the pole. So from here all the way to here, let's call that S. Right? I went to the pole because the question says how fast is his shadow moving relative to the pole. So you really have to think about this problem because it's a little tricky. Imagine that this is the pole, right? And there's a person walking away from me at 7 feet per second. Their shadow is moving away from me as well, right? Okay, so what I see, if I ignore them and just look at their shadow, I just see their shadow moving away, right? Now, imagine you're the person now, and you're walking, and you're looking at your shadow. It's moving away from you too, right? But you're moving as well. So it's not going to appear to you to be moving as fast as the person who's standing at the pole not moving. Make sense? It's important to understand the distinction there between us wanting to know the speed relative to the pole versus relative to the person who's actually walking. If it said, what's the speed of the shadow relative to the person, I would be drawing my S from here to here. Understand? Okay, so we want ds dt, don't we? Okay, when do we want this? We want ds dt at what particular, like when you snap the instant in time, what can you tell me? He's 12 feet from the pole, right? Which 12 in our picture represents which variable? X. So I'm going to say at x equals 12. I think I have everything I need. I think I do. I have the rate at which x is changing with respect to time. I want to know how fast s is changing with respect to time at exactly this moment in time. And I've got a pretty good general picture that has both x and s in the picture. I've got the instant picture. The only thing I don't have in my instant picture is I actually don't know this length right now, do I? Could I find it though, you think? Do you think I could find it? Like if I was in this situation, if I know this is 20, that's 6, this is 12, I should be able to figure out how long that is. I'll have to mess with triangles, but I'm just thinking ahead here that I should be able to find this length if I need it. Okay? All right, so the next thing is, and this is again something that I tried to stress to you last class, it's really important. When you find this equation, right, all it needs to do is connect these two variables together, x and s. And the equation you pick is any equation as long as it's legitimate and it actually fits the physical situation you're looking at, right? And once you find that equation, you are not allowed to fix anything yet. You cannot let x be 12 yet. You have to wait till after the implicit differentiation. That's when you're allowed to stop everything and take that snapshot, all right? And I believe it says, does that say that on the, does it say it on this page? I don't know if it does. No, it doesn't. Okay. It just says on the top, step 5, it says, use implicit differentiation to differentiate the equation from number 4. Your derivative should now include what you're trying to solve for. So, okay, it doesn't say don't plug anything in until after you take the derivative, but I'm telling you now for the second or third time. All right, equation. So where are we going to get an equation from? We need to get an equation off this picture. No Pythagorean, right? A squared plus b squared is c squared. We don't have that, do we? Right?
S minus x?
S minus, okay, so s minus x would be this distance, right? I could label that, yes. I mean, I don't know if it's going to help me, but that's not wrong, right? We should all recognize that this would be whatever s is, take away x, right? So if this was 10, no, let's say this was 30, right? And this was 10, then this would be 20 or something like that. I could always find that, right? I agree with that, don't disagree. What else could we do? I'm trying to get an equation that connects s and s together, x and s together.
1
Right.
squared plus 12 times s minus 12 squared equals the hypotenuse?
No 12, you can't use 12 yet, right? Remember, we can't look here, we have to look here. So look, I mean, we could look at this for a while, okay? This is your first problem that's like this, so I'm gonna just show you, all right? What we're gonna do is recognize, this is not the equation, the implicit, okay? This is scratch work right here, but I'm not gonna erase that. So I want you to see that you have two triangles. You have the big triangle, right? This big triangle, and you have the small triangle. And those two triangles are what we call similar triangles. So this goes back to geometry, some point in your life. They both have a 90-degree angle here, right? And they both share this angle, right? This angle is the same for both triangles, right? This angle right here. And so if this angle is the same for both, and this angle is the same for both, then that angle must be the same for both, right? Because all the angles must add up to be 180. So these are what we call similar triangles. Similar triangles have what we call congruent angles. The angles are the same. And what's important about similar triangles is that whenever you have similar triangles, the ratio of corresponding sides are equal. The ratio of corresponding sides are equal. So I'll explain that more when I draw this, but let's label some stuff here. Y'all agree this is 20 and this side is S, right? You agree with that? And over here, I could label this 6, and then this, that s minus x is actually very helpful here. It's s minus x, right? Questions? Now, the relationship, like I said, because these are similar, the ratio of corresponding sides are equal. So what that means is that I can take any two sides of this triangle and make a fraction out of them, and it will be equal to the same two corresponding sides rewritten as a fraction as well. So I could write 20 divided by s, so I'm going to put I could do 20 divided by s is equal to 6 divided by s over s minus x. I could write that down. That is a true statement because these are similar triangles. Right? Now, is this an equation that has both s and x in it? Yes, right? And that's all I need. Now, I could do it this way, right? Or I could do any two corresponding sides, any ratio I want. I could do this as well. I could do the s over 20 instead and do the s minus x over 6. So I could do s over 20 equals s minus x over 6. I'm free to do it that way. Or I could do, let me do something weird. Let me do 20 over 6 equals, so I took the vertical side of this one divided by the vertical side of this one, and then what I could do is say that that's equal to this long side, this base, divided by this base. So I could say s over s minus x. And there's all these different ratios I could set up. All of these are equations that connect s and x together, right? So I can use any of those. Which one would you like to use? I can see the one I want to use. The second one is the one I would want to use here. And the reason I like this one is because s and x are both in the numerator, right? Here, if I ever differentiate this, I'm probably going to have quotient rule because I have a quotient, right? If I ever differentiate this, well, this is going to be a mess because they're down in the bottom, so I'd have to look at these with negative powers, and I just don't want to mess with that. So I'm going to go with this, okay? Do you have any questions? There's a bunch more that we could have set up, okay? There's a lot of different, I could have done, what else? I could have done 6 over 20 equals s minus x over s. I'm running out. There's not an infinite number of them, but there's more than 2, all right? So I'm gonna go with my equation now, all right? So my equation is gonna be this one. And watch the way I write this equation, all right? I'm gonna write it 1 over 20s equals 1 over 6 times s minus x. So taking s and dividing by 20 is the same as taking 1/20th of s. And taking this and dividing by 6 is the same as taking 1/6 and multiplying it through, right? Why are we doing that? Because I'm going to differentiate it, right? And so the constants, I don't want to look at these as fractions. I want to just look at these as like numbers out in front. It'll be easier for me to differentiate this way, right? Y'all good? All right, that is an equation, yeah? We could take this further. Like we could distribute the 1/6 through. We could get all our s's to one side. I mean, we could simplify this, but I'm happy. Right here, I'm ready to differentiate this. Okay, I'm going to just do it right here. So now the implicit. Y'all sure y'all don't have a question? Yeah.
Would it help to just find the length of the shadow like earlier on?
Would it help if we would have actually found out what this was earlier?
Yeah, just really. I know that like it can't be applied this early, but just like to know that I think would maybe help.
Yeah. So this is a good question. Should we have just found this and just assume we're going to need it later? You could, but it is possible that we don't need it. So then you might be wasting your time. Maybe. So if you do it, it's not going to hurt you other than time, but you may not need it. Let's see. I mean, the derivative is going to tell us if we need it. So we're going to do implicit differentiation, right? Both sides of the equation with respect to time, right? Why? Because we're given speeds. These are, 7 feet per second. We want to know how fast s is changing with respect to time. We want to know the speed, right? So we're going to differentiate both sides with respect to t. Here we go. What's the derivative of this with respect to t? 1/20th comes for the ride times derivative of s with respect to t is ds dt, right? Equals 1/6 comes for the ride. And now, because I have two separate terms, I can take derivative of each one individually. So derivative of s is ds dt, right? And then minus derivative of x, which is dx dt. We good? Yep. That's my implicit. Oh, I meant to put that over here, sorry. Look at this. This is actually pretty interesting because we're trying to solve for ds dt, right? We see that in here, ds dt, we're happy to see it, right? And then the only other thing I need to know, right, or the only other thing I have in here is dx dt, but dx dt is 7, which means, do we need s? We don't need s. This is strange. Somehow, the speed of the shadow does not depend on anything except that. That's pretty profound, but I'll get into that in a second once we, let's do this first and then we'll wrap our heads around what this answer means, all right? So I'm going to take this now and I'm going to solve it. So 1 over 20 ds dt equals 1/6 ds dt minus dx dt was 7, right? Like this. So all I did there is just replaced my dx dt with 7. Now just look at ds dt like a variable. You're trying to solve for it. So I'm going to distribute 1/6 through here. Right, so I distributed 1/6 here, 1/6 here. Yes?
Is the reason you don't need the length of the shadow because the further away he's getting, the longer the shadow's getting?
Is the reason I don't need the
Well,
length?
you don't need to find S originally because the further he gets away, theoretically, right, that shadow should be lengthening. So
The shadow should be getting longer.
yeah,
Right?
So finding S wouldn't really help because that shadow's changing every step he takes. It's getting longer.
It is getting longer. Yeah, let's answer this. We need to talk about that more.
Okay.
Let's answer this first. We'll look at the answer and then we'll see if we can wrap our heads around what's going on here. These both have ds dt, right? Or this is on both sides. So I'm going to move this one over, right? 1 over 20 ds dt minus 1/6 ds dt equals -7 over 6. Is that right? Yeah? How do you do this? How do you put those together? You could factor, okay, factor out, and then we'll get a common denominator. Okay, ds dt, do 1/20 minus 1/6, and then equals -7 over 6. And then for that, 1 over 20 minus 1/6, there's all sorts of different ways to do this. Common denominator though, right, to put them together. What is that? What is it? Should get a negative.
Well, no, the common denominator is 60.
Oh, you're saying, okay, you want to do 60, sorry, okay. So if I do 60, I multiply top and bottom here by 3, so 3 over 60, and minus 10, right, over 60. So -7 over 60. Yeah? Come back over here. I'm going to just put it right here. So we have ds dt times what we just got, which was -7 over 60, equals -7 over 6. How do I get ds dt by itself? Divide or multiply by the reciprocal. You can look at it either way. What's it come out to be? You don't have it yet? If I divide by this, same as multiplying by the reciprocal, you should get 10.
Yeah.
You should get 10. 10 what? Think about what this is. S is the measurement of this distance, right? Which should be feet. And then time is seconds. 10 feet per second. Okay. So let's start talking about what this is saying. This person is walking away from this pole, right? Moving along. The person's walking at 7 feet per second. At the instant this person is 12 feet from the pole, the shadow, the tip of the shadow is moving away from the pole at what speed? 10 feet per second, right? But what's really interesting about our math is that the actual position of x has no impact on this answer, right? So if I would have said, hey, what's happening when he's 20 feet from the pole? Would anything change here? Nothing would change, would it? Because this doesn't have x in it. If he's 100 feet from the pole, it doesn't change, which means that his shadow is moving at a constant rate, just like he is. He's moving at 7 feet per second, and his shadow's moving at 10 feet per second. Even though his shadow gets longer, it doesn't speed up. It's really weird. It's a strange behavior. I don't think it's intuitive to think that that's what would happen, because as you move away, you imagine your shadow starts to really take off. So you think it must be speeding up, but it's not. It's moving at a constant speed just like you are. That's weird, right? Yeah.
Do we have to do one of the guy climbing up a ladder or something going upward?
Pardon me?
Someone going upward versus going
Someone going up. What about it?
like the way the shadow would change, it would still be indirect.
Oh, you mean if we had this person moving up at a constant speed, would his shadow move at a constant speed? Good question. I don't know. We would have to investigate it.
I assume it would take off because it would go and then it would go horizontal to the floor.
Yeah, think about what happens when when the tip of his head gets to 20 feet. Where's the shadow? It can't touch the ground anymore. So if you go a little bit below it, it was way the hell out there, right? So it's to get way out there, as he goes up, to get way out there, it can't be going constant, right? It has to speed up because it's going to eventually become infinite. Now, it'd be interesting to actually do the math and see that, but yeah. This one to me is counterintuitive. I think most people, including myself when I first saw this problem, thought that if he's moving at a constant speed, his shadow's going to get longer, so it's going to start to speed up to get away from him. But it doesn't. It's just moving faster than him, that's all, but it's not speeding up. It's like, you can imagine it really like this now. There's two people, they start at the wall, one's walking at 7 miles per hour, the other one's walking at 10 miles per hour. So the other person's just walking faster. And they're getting further away, right? But they're not speeding up. Okay, good. That only took us 30 minutes.
So the FP code didn't matter?
It didn't matter. It was irrelevant. But how do we know that? This right here. When we did the derivative, right? Nowhere in here did we see x or s. All we had was dx dt and ds dt. Let's do another one. Well, I should just leave this here. General. Let me put the problem up while I erase the board. Now, I apologize ahead of time. I couldn't get this to... I put this on here and I didn't make it quite big enough, so I hope you can read that. I'm sorry? Oh, yeah, the animation. I'm sorry. Yeah. So that's the person walking away from the pole, right? And then here's the shadow in front of them. I don't know if that's the animation you were imagining in your mind, but that's it. Right? So if you look at this, let me slow it down just a little bit. What you want to notice here is that the person